I was worried that competing with the first batch of lunch would have an impact. Either the lunch is really, really bad, or people don't care that much about it. Looking at this room, this is amazing. Still got a minute. Should we get started? All right. My name is Wieck. I recently was joined into Amazon Web Services. That's why this talk, which was submitted before that, has pretty much nothing to do with what Amazon is offering, other than that it's about Postgres. Now, I have a little bit of Postgres history. For those who don't know me, I joined the Postgres community as a contributor in 1996. After already working and hacking Postgres for 2 years. So my first contribution to the Postgres community was fixing the rewrite rule system. And since then, I have contributed things like the numeric data type, bgSQL, the background writer, the statistics collector, foreign keys, Ghost, and I/O. It's always good when you think about I/O to first look at where is my I/O actually coming from. And we start by looking actually at our system topology. Now, if we look at this is just an example of this high gloss manager version that you usually get when you look at the system, because it's not just an application plus a database. You always have to look at a complete system and what its database behavior requirements are. We're not yet talking about I/O, we talk about database behavior. And as we see here, we have browsers and we have some B2B clients that work over an API, and then of course we have maintenance scripts and that kind of stuff, and we have reporting going on. Now, this is of course very, very simplified, because we know, first of all, that browsers, where there is one, there's usually hundreds, if not thousands of them. And B2B clients, exactly the same thing. They never come alone. And scripts, yeah, there might be multiple maintenance scripts as well that run concurrently and stuff like that. So we always have to think about concurrency in this case. But even if we have this picture a little bit desimplified, the first thing that we need to ask ourselves is, what are my behavior priorities? And we'll give you just two very simple examples. If I have an online retail store and those web browsers are my shoppers, then that is my top priority. I want to have consistent response times. I can't deal with response time spikes. There was a very old study done by the University of Lincoln, Nebraska in the late 90s, where they asked what is the maximum tolerable response time of a web application. And they came out with 2 seconds. Why is it 2 seconds? Because after looking for 2 seconds at a screen where nothing is happening, and no, this hourglass does not help, your brain gets bored and looks for distraction. And once you're distracted, it takes a couple seconds to get back into what you were doing. And that is a time delay that you don't want to have in your users. So that drives this, and since that was the late 90s, we now measure response time in milliseconds. Yeah? So then my optimizing goal is to smooth out my transaction response time. It doesn't really matter whether my transaction average is 100 milliseconds or 110 milliseconds. The user will not notice that. Yeah? But if I have spikes of up to 5 seconds in there every couple minutes, bad business. Don't want to have that. The other scenario that we can have is that the B2B clients are my priority. Let's say I'm running a search system that has 100 web crawlers out there that gather data. Well, I need to get 250,000 transactions per hour into the system. That's total throughput. I don't care whether the individual one has spikes, because these web crawlers, unlike the online shoppers, they are not going away. Yeah? They don't close the browser session. They will wait patiently there, and they don't go somewhere else and deliver their data to somebody else. That's what the shoppers will do. Yeah, the web crawlers don't. So now I have my priority being total throughput. And that affects how I optimize my I/O, what I'm tuning towards. The next thing that usually people who draw these diagrams don't tell you, and you always need to carefully ask for it, they talk eventually about legacy code. Yeah, that's the old zoo. I have found in customer installations COBOL programs that came from the mainframe era that were ported to VMS, made it somehow to Solaris, where they got ported to Oracle, and now they want to keep the COBOL code running on Postgres. Right, yeah, that's the old zoo. And the problem there is, since they came from mainframe where they used ISAM files, the COBOL programmer knew exactly how to do a 3-level nested loop in COBOL. And that's why this is not an access line, it's actually Morse code. If you program a nested loop in your application, that thing is talking Morse code and it's trampling over the whole system. Yeah? Last thing, the people who draw these diagrams, I don't know why they always use this cat food symbol in the middle there. Yeah, probably stands for delicious bites. My cat loves those, but they basically should draw it this way because they have absolutely no idea what's going on in there. Yeah, they are just not really honest and admit this. So now that we have our system overview and 2 scenarios that we want to optimize for, let's replace that magical bit container with Postgres. Because really, this magical bit container is nothing but a binary file editor with a horrible user interface, right? That can deal with a lot of concurrency. That's what it is. Now, I hope that pretty much everyone here in the room knows that when you connect to a Postgres database, your session connects to what we call a backend. That is the Postgres process that is actually parsing your SQL, that is creating an execution plan for it, and then accessing the data for you. One important detail about I/O here is Postgres never reads directly from disk. Postgres does not do what some other databases might do, direct or raw device access. It doesn't do it. It always goes through a file system. It relies on a file system to organize the data in the block structure of the disk. That means, consequently, that your OS buffer cache is always involved in Postgres I/O. Yeah? Which to me means that the kernel tuning parameters cannot be taboo. You must have access to them. And I will tell you later in the talk why that is. I have literally fought tooth and nail with system administrators who refuse to change kernel parameters. They come with, but these are the recommended values from Red Hat. No, these are the default values that are meant to work for a large number of different I/O patterns from different application types in a reasonable compromise. Yeah? But when you install from an ISO image, that ISO image has no idea whether you are creating a web server, a network file server, a firewall, a database server, a developer workstation. No. So those are all different scenarios, and you need to tune this to match your needs. Postgres, on the other hand, comes with, let's call it very, very conservative configuration parameters out of the box. You can literally, and I've done it, you can install CentOS 7 on a Raspberry Pi 3, install Postgres on it, and with the default parameters, it will start up and serve queries. You have a running Postgres database on a piece of hardware this size. Probably a cell phone could do it too, if you could run CentOS on it. Yeah? So everybody and their grandmother, pretty much after installing Postgres, has their fingers in the Postgres conf file to adjust that, because those are not good parameters for a server with 64 cores and half a terabyte of RAM. Not really. So, what we also want to look at, since we are already in buffering, the OS buffers are involved, whenever it is about table or index data, Postgres does not read this data into backend local memory. It has a shared buffer area where those reads go into. Yeah? So everything that Postgres accesses in table data is actually loaded into shared buffers. And that has two reasons. One, of course, the data is immediately available to every other backend, every other session, without going to the disk again, or the OS buffers. But the other thing is, there's a little detail here on the slide that from the last row is probably invisible. The arrow from the OS buffers to the backend is directional. Postgres is designed or meant so that the backend itself does not write. It does not have to wait for writes. It loads the data that it needs to modify in an update or insert or whatever. The blocks get loaded into the shared buffers. They were modified there. The shared buffer is marked as being dirty, and the backend moves on. It leaves the dirty data just in there. And there are two other processes, the background writer and the checkpointer, which are supposed to do the dirty work, to wash the dirty laundry and get these dirty blocks out of there. Now, in extreme cases, it can happen that the backend needs to load data and doesn't find a suitable victim for eviction, and then it will write data. Yes, but that is, if that is happening on a regular basis, you need to look into tuning. Okay? Yes?
The checkpointer, does it only write the dirty buffers or the entire page?
Those are pages. When we talk about buffers or pages, blocks, we always mean 8K blocks.
So
yes.
There's nothing like a fuzzy checkpointer where it will only write the dirty one. So
it will write only dirty ones, but inside the smallest granularity of what it considers dirty or clean is 8K.
Okay.
Yep. Good question. Thank you. Yes, please.
If we change the block size, then would it be still 8K or the block size?
The block size of what? then you would change that. I have never seen a good reason to change that block size from 8K. But yeah, experiment with it and do benchmarking, and you will find out. Yeah, I've not experimented with that. So now what's happening is, of course, that's why I left all these scenarios up there, so that we can see them still, our I/O requirements. If we are optimizing for this first scenario with our online shoppers, where we want a smooth transaction response time, I was doing benchmarking with GPCC style workload, and I had optimized my Postgres parameters. Yeah, checkpoint timeout 10 minutes, checkpoint completion target 0.9, a little bit more aggressive background writer, all of that, you know. And since I do benchmarking different from many other people, it's an OLTP load, so I graph my response times at a 10-second granularity, not 10-minute granularity and averaging. No, I want to see the timeline of my transaction behavior, really fine granular. And I saw response time spikes every 10 minutes, right where the checkpoints ended. What has happened? Well, I was searching, tracking more and more kernel metrics, until I found the culprit. Dirty OS buffers. Well, yeah, the checkpointer and the background writer stretch out the write system calls nicely over the 10 minutes, well, 9 minutes, 0.9, right? But since correctly configured TPCC does neither fit into shared buffers, nor completely into the OS memory, yeah, TPCC has a very non-uniform random access pattern, where you have some rows, few rows, that have a tremendously high update rate, and then it tapers out in an exponential fashion. More and more rows get less and less updates, yeah, or write traffic. And so it doesn't make sense to cache the entire database into memory. Some of that lives on disk most of the time. So now the OS is under a constant barrage of read requests. And as long as Linux in the default configuration has OS buffers where it can swallow a write into without pushing it out to disk yet, or let's call this persistent storage instead of disk, yeah? I still talk about disks, it's showing age, I think. Should talk about persistent storage. So, since there is OS buffers available still, the OS does not do the write. It delays it to serve another read, because if there is a read blocking, the process is waiting for the data. The writer is already done. He can continue consuming CPU time. So the OS prioritizes the reads over the writes. Only if you get to a point where your dirty background ratio or dirty background bytes is exceeded will the default I/O scheduler in Linux actually say, I need to start writing. Before that, it doesn't do that. And when I, working on physical hardware, not virtualized or anything, when I changed my kernel parameters so that the dirty background bytes was approximately half of the cache that my battery-backed RAID controller has, all the spikes went away. Yes, my average transaction response time went up 10–15%. I take a performance hit, but that's the performance hit I wanted to take for smoothing out my response times. Yeah?
So I say that you halve the dirty background bytes. That's what you said, right?
No, I said I set the dirty background bytes to halve the cache memory on my RAID controller. The RAID controller, of course, being configured in write-back configuration. that forces the operating system to actually put data over the PCI bus in order to write the dirty OS buffers. Now, what happens here with caching in both instances, whether it's shared buffers or OS buffers, when I am dirtying a shared buffer and another transaction comes around and modifies the same 8K buffer again before the checkpointer or background writer have actually done the write system call, both updates go into one write. The write is not going to disk at that point. A write system call is just a memcopy operation. It copies the data from your user space memory into OS buffers. Yes?
So if we're trying in a cloud environment, like say the EBS, say the provisional IO environment?
Yes, you can do that. You can provision more IO, sure, but that does not make the Linux kernel actually use it. You need to tell Linux also to use it. Just because the hardware or the underlying storage subsystem has more bandwidth available doesn't mean that the OS is going to start using it automatically. Yes?
Is it fair to say that this is the case simply because that Postgres doesn't do direct I/O?
That is related to that. Yeah.
And it's 100% dependent on kernel I/O system call.
Yeah.
So is that going to ever change?
I don't think that Postgres will actually go and do for the data, for heap and index, direct device I/O. I don't think so. Because there are other aspects here. But Graham, you had a comment?
He asked you to repeat the question.
Oh.
The question from back here.
Yes, thank you. So the question was whether Postgres ever will change and do direct disk I/O or raw device I/O, correct?
Yeah.
And I don't think that community Postgres will ever go there. It has been suggested before, and it has been shut down before. So I see a small chance, a very small chance for that. Yeah, it's not going to happen. But there are two more aspects here to this buffering. Yeah, as said, on both levels, whether it's in the shared buffers or in the OS buffers, multiple modifications can actually be folded into one real transfer down to the persistent storage. But there is another aspect. If the OS buffers my writes first and then has to write them out at once, it can do write reordering. It can change the order of these blocks. And believe it or not, even if you are on the best SSDs today, doing ordered writes is better than doing them completely random. Yeah, some of these SSDs are, because of their capacity, are implemented in bank switching technology. Yes, exactly that technology that we had on our game consoles in the 70s. Yeah? Bank switching. It takes time to disconnect chips from a memory bus and put another set of chips on. And so while they don't have really rotating platters, there is something like a seek time. It's still there. It's very small, but it's there. It's measurable.
Much smaller.
It's much smaller, yes, Andrew, but it is measurable. Yeah. So anyhow, so this write reordering is also important. We just don't want the OS buffers in this scenario to gobble up 20, 30 gigabytes of changes, and then comes an fdata sync and it swaps the I/O channel for several seconds. That's what I don't want. And that I get rid of there. One can go a little bit more extreme and configure for the deadline I/O scheduler. That's also a common recommendations when you have I/O problems. I have not experimented myself with that. Yeah, might be worth exploring if you really have I/O problems down there. Yes.
How many of those are dynamic? Like, for example, if I want to change it from time to time, depending on if it's going to be read heavy or write heavy at a certain point of time of the day?
The kernel parameters you can change at runtime. Those, except for the deadline IO scheduler.
Yeah, of course, yeah.
Yeah. But the background ratio, the dirty ratio, and the dirty background bytes, you can change at runtime. The number of shared buffers, you can't. But you can change, for example, the aggressiveness of the background writer. Yeah. So yes, those parameters can be changed at runtime. Yeah. The other extreme that we see here is, of course, if we want to optimize for total throughput. Yeah. At that moment, I need to look at this other parameter there, the dirty ratio. The dirty ratio is the percentage of OS buffers that need to be dirty for the kernel to completely block write system calls. The write system call at that moment, if those many OS buffers are dirty, will block. The operating system will not accept it, period, end of story. That's really disruptive. So if you run a batch load, looking for total throughput, set that thing to 80%. Why not? You don't care about consistency in transaction response time at that moment. You want to get the data in. Yeah? So those are the different optimization rules, just rule of thumb. Yes, please.
So if you're using SSDs, does it make sense to make the random page cost equal to the sequential page cost?
Not equal, but closer to it. Absolutely, yes. All right, that's, however, unfortunately not all the I/O that Postgres does. There's, of course, also temp data. Now, temp data can have several origins. Let's ignore temp tables that are, for some reason, loved by people who do reporting. I don't know why their fascination with temp tables is there. Must have historic reasons. But Postgres also deals with temp files, for example, for large sort sets. And that is good that way, because in the default, when you install Linux, you are using glibc. The glibc malloc free implementation is extremely sticky to memory. It really hates to give memory back to the OS. You basically have to kill the process before it does that, in most cases. There are some system calls that can be done, madvise and stuff like that, but even those results are not really great unless you really have a stack-like behavior of allocating memory and freeing it. It doesn't buy you much. And that means that once a process, a backend, has ballooned to a large memory size, it holds on to this, even though it doesn't need it. And those memory segments are no longer available for the OS buffer cache. So if you are smart and have your database with a connection pool that lets your backends live for a long time, and you have 500 connections to the database, and every one of them at some point uses 1 gigabyte of memory, you run out of memory just because of that. Oops. Because the things on free don't give memory back to the OS. Now, when you do large sort operations, you of course need a lot of memory, normally, to sort the data set. What Postgres does is it accumulates as many rows that fit into one word mem setting and writes a temp file out to disk after using quicksort to sort them. And then, very simplified, it basically does a merge of all these pre-sorted data sets, which, if you are still with the default config parameters, where you had your dirty background ratio of 20% and everything, basically means that sort is done in a couple milliseconds or a couple hundred milliseconds. Chances are that the OS IO scheduler didn't actually write the data out yet. It's just sitting in OS buffers. and now the sort is done, you delete the files, well, Postgres deletes the files, and the dirty OS buffers get thrown away without ever making it to disk. But hey, we just tuned the kernel to smooth out our transaction response time. There's a conflict of interest here. Because now I forced the OS to be more aggressive and write out my sort set. I have not found a cure to that one yet. Sorry. I haven't found the cure. But yeah, eventually the cure would be if you really know I have certain processes or certain business transactions that cause memory ballooning, put them onto their separate connection pool that is short-lived, let them balloon with a larger workmem setting, and solve the problem that way. This is really an administrative problem at this point, because I don't know how to solve it in Postgres at this point. Yes?
Are the parameters that would control that, are those specific parameters overridable on sort of at a session level? So you could do that for a given state?
Yeah, the question is if those config parameters are modifiable on a session level, and the answer is yes. Workmem, maintenance workmem, pretty much everything that affects the query optimizer is actually session tunable. Yes?
But aren't the, I don't know if OS buffers are also tunable on a per disk basis? So if you had different...
I don't think so.
Okay.
So the question is if OS buffers or these kernel tuning parameters are available per disk, and I don't think they are. Please?
So if you put sort on a separate disk, you have different file systems. There are advantages of different file systems on how fast they are. So when you showed those experience before, so you can put sort on your fast disk.
Can you put sort the temp file the temp table space? Does that contain the sorts?
I think so.
Yeah. So yeah, you could do that. Could experiment with that. Absolutely.
Yeah, when you set a different default table space or you have a table space, it is your temp table space. Initially, even if you don't create temp tables, because the things that do spill to disk, like you're talking about,
Go in there.
they will start going there instead.
Cool. Thanks.
You know.
And you can actually have multiples of temp table spaces, so it could actually spread the.
Multiple temp table
I think
spaces.
I think you can.
Yeah.
Yeah.
You can get really creative, but do you really want to maintain such an installation? No. Right. Me neither. I would like to have a more systematic approach to solving this problem. I'm going to search for it. Yep. All right, and then, well, the other part of I/O, the dark side. We said we are throwing the changes that we're making just into shared buffers and leave them there for later to be written out in order for that to be crash safe. By the way, the slide sets will be available. I will upload them after the talk to the conference site. Yep. To be able to do that, Postgres writes what we call write-ahead log. It's basically a log of changes that allow us, in the case of an OS or Postgres crash, to redo the operations to basically recover from the crash and rebuild the data, the updates that were lost in shared buffers and OS buffers eventually. Yeah? Now, write-ahead log has a very different I/O pattern. First of all, most people think it's sequential writing. It's not exactly sequential writing, because really like an OS crash in the middle out directory, this curious little thing, yeah? And you would find basically files in there. And if you just were in the middle of extending a relation, the indirect block might not have made it to disk, but you wrote the data blocks already, and those data blocks would get lost in the following file system check. Because of that, Postgres tries to minimize metadata changes at runtime. And so under a system that has a relatively steady load, Postgres is recycling, reusing those write-ahead log files, these segments. Those are 16 megabyte segments, and you do yourself a good favor if you configure enough wall size to have pretty much twice your checkpoint timeout covered. Yeah? But in any case, if Postgres needs more wall space, it will create another segment. Yeah, you can't really prevent that. It will start an immediate checkpoint under high priority if that happens, but it will eventually allocate another wall segment. Yeah, and in order to now avoid that to turn into read operations on the wall files, Postgres always pads the write to wall to the next 8K boundary and then seeks backwards and writes from there again. Because if you give Linux a complete 8K block on an 8K boundary, it will not have to merge the old content of the file with the partial new content, so it doesn't have to read. It can simply overwrite it blindly, and that's what it does. So if you would change that, you would see reads and rotational delays on your wall, and that's really killing it. Yeah. So in that way, Postgres is not really sequentially writing. It's more like 3 rungs up, 2 rungs down on a ladder. A good storage subsystem will actually turn that into sequential writes on the permanent on the persistent storage media. Yeah, which is why you want good storage I/O subsystems. Now, there is one other thing with respect to wall. Wall has a very, very high fdata sync rate. On Linux, the wall files are actually opened by default in ODirect mode, so that a write implicitly is flush to disk. And that, if it's sitting on the same persistent storage, interferes logically. Because now you really have a high pressure, completely synced write load that needs to get down no matter how many read IOs you want to make. Yeah? So if you have the ability, that of course requires that you basically run your own hardware and are in a bare metal environment. Because I have not seen any virtualization or any virtual cloud system, even in-house clouds, that allow you to put multiple I/O subsystems for virtual machines. It's impractical. No system administrator will want to maintain those VMs. It gets, from the administrative overhead, it gets cost prohibitive for cloud. But if you run on bare metal, consider running this thing on its own storage subsystem. It can really boost your performance. There is one other, yes please?
Is there parameters to do that, or you just have to do it with the operating system, like a small?
You just, the question is whether there is a parameter for that. No, for the xlog, there is no parameter for that. The normal procedure is to move your pgxlog directory to a different mount point and then put a symlink there in place. There are parameters for where the postmaster error logs and stuff like that go. Yeah, those are the recommended things. In a real production setting, I think you normally want them to go to syslog anyway. Yeah, so symlinking is still state of the art in this case. But even if you can't move the xlog to a separate mount point, there is still an advantage of making it its separate file system. I meant IO stop system. File system is still a mount point. So that is when this case happens and Postgres wants to, yes, thank you, wants to extend its wall size. And you get the dreaded no space left on device while it's writing wall. Postmaster will commit suicide hard, and most likely your database will not start up again before you made more space available. And I have seen everything under the sun, people deleting files in pgdata just randomly. Yeah? Including this dreaded pgx log or C log. It's both catastrophic. Yeah? You don't want to go into there. Now, if your file system runs out of disk space when you're writing data or a temp file or anything like that inside of pgdata except for pgx log, that one session gets a transaction aboard. Your database is still up and running. It's very, very crippled because pretty much all write operations will fail unless your scenario is really somebody did a very, very bad query that tries to do a self-join 5 ways of a humongous table that needs several sort operations at once and basically balloons your temporary space needed to 3 times the database. Well, that will fix itself that way. That problem, that process will run out of space, will abort, will delete all the temp files, and problem gone. Until the user hits the same query. Yes. So there is still advantage of putting the xlog on a separate file system just to avoid complete panic, because growing file systems is easy as long as you have spare volume group space laying around. Shrinking them is hard, at least in my experience. Yeah? So, yes, Andrew.
You need to be careful if you put the write-head log on a separate disk, because usually it's going to be a lot smaller.
Yes.
And if writing if your archive command blows up or something like that, it's very easy to run a small disk out of space with write-ahead log.
Right.
So
right.
you need
want to be
you
careful.
need to be
there.
very careful.
Yes.
I've seen that happen lots of times.
I totally see that. Absolutely. So, and now, since we are kind of running short of time already, there's of course more I/O going on, and you really, if you want to optimize your system, this is not the end of the wisdom. Yeah? You need to consider, do I have streaming replicas? Do I have logical decoding going on? Because then I have wall senders. Do I have my backup system correct? Yeah? With large installations, nobody does PG dumps anymore. So if you are considering writing your own backup scripts, please don't do it. Yeah, there are people who have done it. David Steely from Crunchy Data has done a great job writing PG backrest. I've used it in several projects. It's wonderful, stable, and so really, do yourself a favor, use something that's tested and has a larger community than your own homegrown scripts. But yeah, all those I/O requirements go into that same stuff. Yeah, because normally when you look at the wall senders, if they are caught up, they read out of the shared wall buffers. Yeah? Once they fall behind, they need to have access to the redo logs on disk, or even worse, to the archive logs, and so on. So there's a lot to consider here. What are my strategies with my streaming replicas and stuff like that? How do I configure them? But that is basically a whole different topic for another talk. Thank you. Any further questions? Yes?
So are there any comments about, say, the share buffer size? Say, sometimes I see people take extremely small
small.
Yeah.
Sometimes people say maybe extremely big.
Shared buffer size, any recommendations? The community wisdom used to be start tuning at approximately a quarter of your available memory. With machine sizes going strongly towards 1 terabyte of RAM, I think that's too much. Because there are operations like the clock sweep, like a drop table, and so on, that require a full scan of the OS buffer cache, of the shared buffers. So with constantly growing machine sizes, I think a quarter is more the maximum than a good default starting point. But again, it really depends on your data distribution, your I/O pattern. There is no one size fits all because we have way too many different requirements.
So the mod table you use say you do the read, for example, should you have bigger share buffer? Because say for example you have 10 table and all is heavy I/O, right?
It can't be answered that generic, and that if you have that many tables, that much data, you need this many. It's not a simple function. Unfortunately, I would love to give you a number, but I can't.
So where the 25% come
from? Anecdotal.
Okay.
Anecdotal wisdom.
It's just a heuristic. It's not.
Yeah.
There's no. It just came from experience that this was often a good place to start. It wasn't.
Yeah.
It wasn't. This is the rule. It was start here and tune.
Yes, really.
But there is no limit on Linux. Because
with the new way Postgres allocates shared memory, there is virtually no limit. You could even go into swap space with the shared buffers, which is not a good idea necessarily, but you could if you really are desperate.
Is there a limitation of sizing the work mem? If you have anything greater than 1 gig?
Nope.
Is there a limitation?
Yeah, there is some arbitrary limit, but you don't want that to be that big anyway, because it can be multiple allocations per backend. So that's per connection, multiple allocations of that. You set that thing to 1 gigabyte, and then you have 200 connections that need 2 of these allocations each. It's 400 gigabytes.
Right, for a scenario like we have a data warehouse where you have batches, and limited number of batches that are running.
Okay, there.
We would require something big.
There you can. It's a session parameter.
But yeah, it's a session parameter. But the question was that if, I mean, we came to know that it doesn't utilize the work mem beyond 1 gig. Is that true or no?
I would have to look at it. I don't know off the top of my head what
It depends on your query, because if your query is using lots of buffers, it'll use multiple instances of work memory
The maintenance work
in a
mem.
for a single query.
No,
Right.
Work mem itself requires more than 1 gig, but I came to find out that yesterday that 1 gig is the most that is going to be allocated. Everything is going to be spilled to the disk.
Really?
After. So
May
I just
not
want to
be
know if that's a
accurate.
true limitation by Postgres or not.
I don't think so.
The vacuum has a 1 gig, had a 1 gig sling, which was just
But that's
patched
the
out.
maintenance workman.
Right,
Yeah.
of the maintenance.
Yeah,
Maybe
yeah.
that's what they were talking
Yeah,
about.
I was talking about work mem. What about wall buffers? Is that something you talked about the wall senders? Is that the sizing of the wall buffer? Does that really impact?
It can. It can because by default, inside of a transaction, the backend will not actually write the wall. It just throws it into the shared buffers, into the shared wall buffers, and then the wall writer is supposed to write them out, yeah, in parallel to it. Only when the backend basically does not find any free space in the wall buffers does it have to write. Or when it hits a commit, then it will try to grab the wall writer lock and write it out, write as much as there is, which can cover multiple commit records from other sessions.
So it would make sense in that case is to have a larger wall buffer if you
Yeah.
have like batches to be.
If you have larger transactions that create a lot of wall, yes, it makes sense.
All right. So the two trigger points are the commit and
Running out of wall buffers.
those are the two trigger points.
Right.
That makes sense. What about the you talked about the OS buffers? What about the effective cache size? Is that something that has an it's usually gauged towards the free mem that you have available, but
That's just a planning parameter. Isn't
That's a
it?
planner parameter.
Yeah, it's not actually
basically-
grabbing that memory.
It's
That's-
an informational parameter for the query optimizer to know approximately how much memory is effectively used for caching on the machine.
So the confusing part
It's
is
the effective cache.
Yeah, the effective cache size.
But the confusing part is that when we have the cache, the shared buffers, which are going to be storing the tables and caching the indexes, why are we putting in? Why are we giving that information about the free cache that is outside of the shared buffer, which is not going to be used?
Because the optimizer will use that to calculate what is then the random page costs and stuff. Yeah, because from that it tries to derive how much of the data that I'm actually reading I will hit in the OS buffers to make a good guess about that.
Is there a way to measure it, like how much actually allocated or how much used, so then we can tune that thing? It's like, okay, are we over or under?
I would love those parameters to be more self-tuning, that the system would figure it out.
The trouble is that you might have other stuff running on the machine eating up lots of memory. So you can't just look at okay, I'm using this much memory and there's this much shared buffers, and I'll say the rest is effective cache I/O, because it's not.
No.
So that's why you have to tell the machine how much you expect to be available for OS buffers. That's what effective cache size is about.
Postgres could periodically look at the OS theoretically and say, okay, I have that many OS buffers and this much free memory, so that's my effective cache size. But that gets OS specific, and Postgres does not. The Postgres community does not like OS or distribution specific code. It needs to be generic. And since those
so that would have to run on Windows and FreeBSD, and so that would be a real pain in the neck.
It's unlikely that the Postgres community will make that self-tuning depending on what you can find in your proc file system. That's why it's a tuning parameter where you have to make the guesses.
Does the Postgres that like the rack work on like a raw file system, so like cook file system, something like that? So it's like eliminating OS buffer and has the Postgres control know exactly what I'm doing. I'm bypassing that.
As said, it has been proposed before. Good luck. Good luck. You need to grow a very thick skin if you want to propose that on hackers.
I'm just asking.
All right.
Quick question.
Yes.
You creating a temp tables.
Yeah.
Right. So we inserted like 100,000 rows in the temp table.
Yeah.
As we delete them, will it increase the memory or still it holds the memory?
If you delete them out of a temp table, I think you would have to truncate it.
No, we can drop the temp table.
Yeah, then
it's
the
if
allocation
it is not
is gone.
dropped, but if the table is created and we use those memory to load 1,000 and delete that rows, will it release the memory for that 10,000 rows?
Well, do you delete this or do you truncate the table?
No, not truncate, delete.
Delete.
Yeah.
Probably still hold.
Yeah. Would still, because even though these are temp tables, they still are transactional.
Yeah, they still have Xmin and all that stuff. Yeah.
Especially the CMIN.
So it still holds the memory you're saying, even though we delete them.
The disk space is still allocated.
Okay.
Essentially, because temp tables don't go through shared buffers; they go through temp buffers, and they are processed locally and much smaller. So you will have that data laying around on your file system. Whether it's already on the persistent storage or not depends on how aggressive you configure the kernel. It's complicated. Yes, it is complicated.
Because we use a lot of temp tables and we load tons of data in the temp tables.
Yeah.
So we
Well, normally one way around it would be to create the temp table with on commit drop. and then it will actually.
On, yeah, in some places we
Yeah,
do on
yeah.
commit, we drop them.
Yeah.
But if multiple users are using that particular functions, and if it is keep creating it, if temp tables exist, that one takes lot of time.
Yeah.
So we don't want to use that at all. Creating a temp table every single occurrence.
Or you
so
leave it for the duration of the session. Yeah, that's gonna sit there.
Yeah.
Yep, definitely.